a new video on properties of isomorphism. The first property, the statement is given here. Suppose phi defined from the group G to the second group G cap be an isomorphism. Then phi carries the identity element of the first group to the identity element of the second group G cap. We know that the groups have identity elements. So what does the first property mean? It means that the identity element can always be mapped to the identity element in the second group. See the figure, it is described here in the figure. The group G and G cap. Phi is different from G to G cap. And then the identity E, here E is the identity of the first group. E cap is the identity of the second group. Then the function phi must map E to E cap. How can we prove this? So let E be the identity of the first group and E cap be the identity of the second group. Then we can write E star E. Here the star operation is the binary operation in the first group. Then E star E equal to E. Where then we know that here E is the identity element of the first group, and in this star is the operation, binary operation in the first group, and E is the identity element in the first group. So E star E equal to E in the first group. But we also denote the binary operation in the second group by star cap. See, star cap, star and a cap is used. Star cap be the operation, binary operation in the group G cap. Then phi of E star E. Then we have phi of E star E equal to because E star E equal to E, therefore phi of E star E equal to phi E, phi of E, and and therefore we can write it as we can split it. The left hand side can be split and to get this phi E star cap phi E, phi E star cap phi E, because phi is the isomorphism. So phi E and using that the property that it using the condition that isomorphism preserves the binary operation. Therefore, phi E star cap phi E we can write, and that equal to phi E. But this phi E equal to E cap. And here on the left side we can write the first phi E, we can keep it, and then star cap. After that the second phi E will be replaced by E cap. Okay, and then even after that, after this step, you can then pre-multiply both sides of this expression. You can take this expression and the last the rightmost expression, they are equal. Then we can pre-multiply both sides by phi e, the inverse, whole inverse. That means the inverse of a phi e. We take the inverse of phi e and then we multiply both sides by this quantity. So phi inverse star cap of phi star cap phi equal to phi inverse of star cap of phi star e cap. Phi star cap e cap. Then what happens? These two acts and then nullifies. The inverse nullifies the effect of phi. So this can be taken together and we get that E cap there. It operates and gives us E cap, and then star cap of phi E equal to, here we have again E cap, then star cap of star cap. Inside this bracket we get E cap, and the operation star cap, then E cap. Thus simplifying this, we get that phi of then E cap star cap of E cap. This happens in the second group. E cap is the identity element in the second group. E cap and star cap, the element phi equal to we get equal to phi e. It becomes phi e, and here we get it E cap, and hence we get we can thus we can complete the proof. Second property, for every integer n, and for every group element A in G, for every integer n, we consider integer n, and for every group element A in G, phi of a raised to n equal to phi a the whole raised to n. Phi of a raised to n equal to phi a the whole raised to n. Okay, but we the proof and whole proof of this property has two sections. The first section, in the first section, we assume that n is a positive integer. Initially, we assume that n is a positive integer. Then, when after proving that case, in the case of a positive integer, we consider the case when n is a negative integer. When n is a negative integer, then you can take that minus n is a positive integer. When n is negative, when n is negative, then minus n will be then positive. And then, since minus n is positive, then you can treat that situation just like the case of a positive integer. So the second part, the proof in the second part will be very similar to the first proof in the first part. So we can think about the proof of the first part. We take phi of a raised to n. Once again, I repeat that n is positive here. So that this a raised to n can be written as a star, a star, a star. How many times? N times. So inside phi, when inside phi, then bracket, inside the bracket, a star, a star, a star, n times. Then that can be split to obtain phi a. Can be split to get phi a, then star cap, phi a, star cap, etc. Okay, since phi is isomorphism, it splits this expression in phi a star cap, phi a star cap, etc. How many times it will be there? Phi a will be, how many phi a will be there? N phi a will be there, and therefore phi a, taking all them together, you can write that phi a the whole raised to n. And this element is in the second group. Okay, then the third property. Third property states that for any two elements A and B in B in G. So this is B actually, and it is not BE. For any two elements A and here this must be read as B. B in G. Two elements are taken and B in G. A and B commute if and only if phi A and phi B commute in the second group. See, any two elements of the first group commute if and only if the corresponding images in the second group commute. That is the meaning of the property, third property. First, suppose that to prove this, suppose that A star B equal to B star A. That means A and B commute in the first group. So A star B equal to B star A. Applying then we apply phi on both sides. Applying on both sides phi, we get phi of A star B equal to phi of B star A, because A star B equal to B star A, these quantities are same, so you can apply phi on both sides. Then using isomorphism condition, yes, isomorphism property, then we get that it then spreads. Then you are then here when it splits, you are in the second group. So when you come to the second group, you are then taken to the second group when phi is applied to each element. Then we get that phi A star cap phi B. Phi A star cap phi B. Similarly, we here on the right side we get phi B star cap phi A, phi B star cap phi A. Therefore, phi A and phi B commute. And to prove the converse, we suppose that phi A star cap phi B equal to phi B star cap phi A. Phi A star cap phi B equal to phi B star cap phi A, and this happens in the second group. And then you can combine this. Left hand side can be combined and write that it is equal, since this quantity equal to phi of A star B. So this is phi of A star B, and this is then phi of B star A. Phi of A star B and phi of B star A. And since phi is 1 1, see, we know that phi is 1 1. It's an isomorphism, so it's 1 1 and 1 2. Okay, since it's an isomorphism, it is 1, must be first of all 1 1, and therefore you know that directly we get that A star B equal to B star A. Since phi of AB equal to phi of BA, we have, since it is given that phi of A star B equal to phi of B star A, then we get that A star B equal to B star A. Therefore A and B commute. Now we have the fourth property. It states that G is abelian if and only if G cap is abelian. Okay, the group G is abelian if and only if the second group is abelian. See, here we have to use directly the property, the previous property 3. The property 3 can be directly used here to prove this. We know that A and B in G commute if and only if phi A and phi B in G commute. So, so you know, so G is abelian if so G is abelian if and only if G cap is abelian. So due to this property, applying this property, easily we can say that G is abelian if and only if G cap is abelian. Along with the property 3, the property, which property is that? Okay, phi of A. Oh, yeah, mainly the property 3 is used to prove the property 4. And so we have to discuss. Now we have to discuss the fifth property. Fifth property, what the statement is, uh, isomorphism. The property states that isomorphism preserves order. Its short form is, or the property can be shortly stated as. In the simplified form, it states that isomorphism preserves order. What does it mean? If order of if order of the element A is suppose n, and then order of phi A also equal to n. So that means order of A equal to order of phi A, or order of phi A equal to order of A for every in G, for all A in G. This is true for all in A in G. We know that A raised to n. So see, if n is the order of A, if n is the order of A in the group, in the first group, then we know that A raised to n equal to, we know that A raised to n equal to E. Then A raised to n equal to E, if and only if yeah, if n is the order of the element A, then A raised to n equal to E. But you know that A raised to n equal to E, if and only phi of A raised to n equal to phi A the whole raised to n equal to phi E. Phi E equal to E cap, the identity in the second group. So phi of A raised to n equal to once again we repeat, once again, yeah, phi of A raised to n equal to phi A the whole raised to n equal to phi A. What does it mean? This statement, the second statement says that so A has infinite order if and only if this means that A has infinite order if and only if phi A has infinite order. So and then using these two statements, with the help of these two statements, we can say that A has infinite order if and only if if A has infinite order. And next, suppose that order of A equal to n, and then A raised to n equal to E in G, and therefore phi of A raised to n equal to phi E, that equal to phi of E equal to E cap in G cap, and that equal to phi A the whole raised to n. But again, this quantity equal to phi A the whole raised to n, that's equal to E cap. Therefore, phi A the whole raised to n equal to E cap. Therefore, this straight away says that when 0 is less than, see, we know that order of every element must be a number, which is greater than, yeah, it is of order of a number having finite order. See, it is greater than 1. It's a positive number. So we can write that 0 is less than order of phi A. There is one number which equals the order of the number phi A. But this fact says that this statement, last statement says that it's order of phi A, because order of phi A the raised to n, phi A raised to n equal to E cap. So order of phi A must be a number less than or equal to n. So this quantity must be order of phi A must be it can be maximum n. and therefore we assume that the order of phi equal to t. Let's suppose that order of phi equal to t, and this t is less than n. Suppose t is less than n, is the order of a phi a. Then phi a raised to t equal to e cap. It is then very clear that phi a raised to t equal to e cap in g cap. Therefore phi a, this quantity can be written as phi of a raised to t. So phi of a raised to t equal to e cap, equal to phi a. So phi of a raised to t equal to e cap, equal to phi a in g cap. Since phi is 1 to 1, and since phi is 1 to 1 and 1 to 1, we get that a raised to t, therefore we get that a raised to t equal to e. I mean, applying the one-to-one nature, one-to-one property of the phi, the isomorphism phi. Using this, the fact that phi of a raised to t equal to e cap, we get that a raised to t equal to e in G. Therefore, a raised to t equal to e. Therefore, this means that it means that t is less than n, and this. Okay, and therefore the value of t is less than n, and this and suppose that, see, a raised to t equal to e. Suppose a raised to t equal to e, and also suppose that t is less than n. So in a previous step, we must assume that t is less than n. We have to suppose that we must suppose that t is less than n. And if t is less than n, what happens? Since a raised to t equal to e, that contradicts the fact that it contradicts the fact that order of a equal to n. Actually, order of a equal to n. So that means t cannot be less than n. So if t is less than n, if we assume that t is less than n, then what happens? So using the statement a raised to t equal to e, it states that there exists a number t which is less than n, and when the power of a is raised to that number, we get the identity element in the first group. So that means that implies that order of a is some quantity, some number less than n, and that's a contradiction, because we have assumed that n is the order of order of the element a, because n is the order of the element a according to our assumption. Therefore t cannot be less than n. Therefore t must be equal to only one possibility there exists, therefore that t equal to n. Therefore order of phi n equal to n. Okay. And next property, the sixth property, G is cyclic if and only if G cap is cyclic. G is cyclic if and only if G cap is cyclic. Suppose that G is cyclic. Then there exists, we know that by the definition of cyclic groups, there exists an element A in G such that G is generated by that element. G is equal to the cyclic group generated by A. G is equal to the group generated by A. And then we know that A is called the generator. And then in a different way, we can say that the elements of, we can list all the elements of the group G. They are all listed here: E, A square, etc. And different powers of A are taken up to the nth power, A square, etc. to A raised to n is the last number. See, it is generated by and where, but there is one correction. See, it is a raised to n minus 1. The last number is a raised to n minus 1, because a raised to n equal to when when the number a has order n. If a has order n, then a raised to n must be equal to e. A raised to n equal to e, and therefore the numbers are e, a square, etc. to a raised to n minus 1. The members of the group are exactly a raised to n minus 1. There is a correction, and this power must be n minus 1. And therefore, and then we can think about the We can now think about the second group, G cap, the second group. And the second group, we know that the it's isomorphic image of the first group. Second group, G cap, is the isomorphic image of the first group. So the elements of, directly you can write using these elements, you can write the elements of the second group. They are, and then phi e, phi e, and phi a square, etc., etc. The last element is phi of a raised to n minus 1. Actually, correction, not a correction here. This is not a number, n, it is actually n minus 1, a raised to phi of a raised to n minus 1. And then we know that phi of e equal to e cap, then phi a, you can write it as, yeah, you can write it the same as the same element. Then but phi of a square equal to phi a the whole square. Next element is phi a the whole cube, etc. Then phi a the whole raised to n. Last element is phi a the whole raised to n, phi a the whole raised to n. And thus this shows that phi a is the generator of. So from this, see, from this arrangement of the elements in the second group, we can say that phi a is the generator of G cap. Phi a is the generator of G cap, and its order is n. Okay, so G cap can be considered as a group generated by the element phi a having order n. Conversely, suppose that G cap is cyclic. To prove the converse, we move to prove the converse. We assume that G cap is cyclic. Therefore, there exists an element x in G cap such that G cap is generated by the element x that equal to E cap. First element is E cap, then x square, etc. to x raised to m, where m is the where m is the order of C. There also one correction: when m is the order of G, then the number will be m minus 1, x raised to m minus 1. See, thus here we have x raised to m minus 1. We must take x raised to m minus 1 when m is the order of G. Since phi is an isomorphism from G to G cap. Since phi is an isomorphism from G to G cap, then there exists an element E in G such that phi of E equal to E cap. So there exists an element A in G such that phi A equal to X. Okay. Therefore, there must exist an element A in G such that phi of A equal to X. And then phi of A square equal to phi A star cap phi A equal to X star cap A X. X star cap x equal to x square, and phi a the whole cube, phi of a cube equal to phi of a star equal to phi a star cap equal to x star cap x equal to x cube. And then you can repeat in general phi of a raised to I equal to x raised to I, phi of a raised to I equal to x raised to I. Finally, we can write phi of a raised to m minus 1. If m is the order of the group, then the power must be m minus 1. So phi of a raised to m minus 1 equal to x raised to m equal to okay. Then yeah, if m is the order, if m is the order, then a raised to m equal to x raised to m, and this is correct actually. This is correct because there are m elements in the group. So phi of a raised to m equal to x raised to m equal to E cap. And therefore a raised to m, by using the one-to-one property, of phi, we get that a raised to m equal to E. Clearly, G is generated by the element A. Okay, we have the summary of this discussion. See, G cap, if G cap contains elements E cap, x square, x cube, etc. to x raised to m, and we have G, the group G, E, A square, A cube, etc. to a raised to m, then phi is defined from G to G cap. Okay, thank you for watching.